My name is Rouslan Svintsitski from French company 3D Ceram. I'm sales area manager in this company. I have more than 30 years of experience in advanced ceramics, and I will just introduce shortly our company before starting to speak about this new additive manufacturing materials for dental area, for dental field. So our company is located in France, Limoges. Limoges is a European center of ceramics because we have a big school of ceramic engineers in Limoges and also the Institute of Ceramic Research. So a lot of companies were created around different ceramic application fields in this city, and we use the opportunity to have skilled human resources and scientific research center. Company was developed in 2001 by two ceramic engineers. We started the company with the printing, so we're a service provider first, and one of the first of the applications for this company was biomedical materials, dental, but also orthopedics, maxillofacial surgery. Now the company is about 30 people. We have moved into a new building 2 years ago where the manufacturing facility is located, but also the materials development center and the application development center. The company belongs to big Japanese group Sinto, about 4,000 people and $1 billion US of turnover. We are present in different countries. We have also the resellers in Emirates and Middle East, company Promec. So usually we have also subsidiaries in USA, in China, and we have installed already more than 50 industrial printers all over the world. Company 3D Ceram is the process provider. What does it mean? So we manufacture and develop our own range of 3D ceramic printers. We develop our own slurries, oxides, non-oxides for different applications, among which is biomedical applications, of course. We have developed our own software, which makes easier the preparation of the printing process and the arrangement of the parts on the printing platform. And we also accompany our customers with the dedicated services which go from training, installation, commissioning, but also the development and co-engineering of some parts or applications for their specific needs. Just a short video about what is the technology that we use. So the technology we use is called stereolithography, so SLA, for ceramics printing, and we print advanced ceramics. It means the ceramics which are used for the heterogeneous properties. Short video just to understand how it works. So as a raw material, as a feedstock, we use a slurry, which is the mix of ceramic powder and photosensitive binder. So this mix, it has a consistency of yogurt to drink, is dispatched by the recorder you can see on the picture on the printing table. Layer by layer, we dispatch this material, like you can see in the machine now, and to make it shaped or to make it hard, we use a UV laser of 405 nanometers of wavelength to cure each point all over the surface of the printing. And the parts are built layer by layer from the down to top. And then when the printing is finished, as you can see it here, the parts, the shaped parts are already printed and have to be post-processed. Because the 3D printing is just the first step of the whole process. When you have the clean part, you clean it, you have to debind it and to sinter it. And only after sintering, you have the ready to use part. Here you have the example of the foundry core. used in investment casting, but it can be dental crown, it can be dental implant, it can be skull implant, etc. So debinding and sintering allows debinding to remove the organic material, so this binder which was mixed with the ceramic powder, and the sintering welds the particles, ceramic particles between themselves to give these final properties to the ceramic materials. Now about this very application. We are speaking zirconia. Zirconia, you people involved in this field knows that zirconia is one of the biomaterials used for its biocompatibility, for its strengths, for its inertia, for chemical reaction. It's used a lot for orthopedic and dental implants, more and more for dental implants, in fact. First, we used alumina, but starting from 90s, we use 3% yttria zirconia. It was used up to early 2000 because what happened that we noticed some aging issues with this material. What kind of aging issues? In fact, because of yttria, we create oxygen vacancies in this material, and under the impact of low temperature and water, which is typically the ambience, the environment inside of the human body, there is the degradation of the material, slow degradation, but degradation. That's why we and our colleagues, our competitors, other people involved in this field, start to use slightly different materials: alumina toughened zirconia, zirconia toughened with alumina, and now we will speak new material which will fix these issues of aging that we have developed with together with the laboratory Matéis in France and the Institute INSA in Lyon in France as well. Here you have this degradation, low temperature degradation explanation. It acts on the structure itself of the material, and when you can see the left bottom corner of the picture, the picture of the orthopedic of the femoral heads, the failure, which was noticed in 2001, and which was caused by this low temperature degradation. So the roughness of the surface of the part is degrading, and it brings to the total damage of the implant, which is not good for the human body, of course. When you have some cracks, when you don't have the reliable structure, you cannot implant these kind of parts. Of course, zirconia itself is, it's called also ceramic steel because it's wear resistant. As I told before, it's biocompatible. It has perfect mechanical properties, strength about 1000 MPa, and it has some toughness. But as I told you, in very early 2000, it stopped due to some breakages and damages of the implant we had to understand, to explain, and to remedy. When you do the simulation, and this is done in this field, of this aging of 3% yttria zirconia, we can see that usually the test is done at 134 degrees C, and depending on the time you see this degradation, you can calculate the theoretical extrapolated time of aging for low temperature at 37 degrees human body temperature. And you can notice that 3% yttria zirconia lasts less than 10 years. You can see this on this diagram, which is in the right bottom corner of the slide. So how to fix this issue with the aging of 3% yttria zirconia? There were several approaches. First, as I told you, starting from early 2000, and people is still using these materials, we developed some materials which are combination of alumina and zirconia. Alumina toughened zirconia, or zirconia toughened alumina. But these formulations still use yttria, which is the main issue in this formulation, and yttria will lead to the aging. So that's why we had to replace yttria by some other doping agent, which was, and this agent was identified as cerium, because the calculation of the aging time with cerium gives very nice results. We are speaking about 400 years of aging extrapolated to the human body temperature at 37 degrees. But what about other properties of this material? Because aging is okay, but as I told you, zirconia was used for wear resistance, for the toughness, for the strength. So do we keep these properties with the new material? To do this research, we did a cooperation program, research program with the laboratory Matthias and Lion Institute in SA. All of this was supervised by a National Research Center in France, CNRS. So the main goal of this study, which were also managed by Mr. Jérôme Chevalier, known in this field, in the field of ceramic implantology, we had to develop new ceramic material for orthopedic application, which will have less aging issues than traditionally used in zirconia, but which will have also same or equivalent properties that traditionally printed or casted zirconia. So the traditional conventional method, which is mostly used in this field, is called isostatic pressing, CIP. So this was our reference to develop the new material, not only for the cold isostatic pressing, but also for additive manufacturing. Because additive manufacturing, as you may know, brings a new dimension into this field. We can do very fancy shapes with no tooling in very fast time comparing to the conventional process. Our company, as I told you, is a process provider, so we are developing our own mix, and we have dozens of different oxides, non-oxide, using the different fields. For medical use, we developed alumina, very high purity, very fine alumina, for example. We have developed alumina toughness zirconia, we have developed zirconia toughness alumina, we have developed zirconia, we have developed hydroxyapatite, bone substitution for the bone implants, skull implants, maxillofacial surgery, orthopedics. We developed TCP, tricalcium-phosphate, used also for the same needs, it's resorbable material. We have also developed some non-oxides, used more and more in this field, implantology, which like silicon nitride. So we have some experience, skill, and expertise for development, and that's why we were asked to accompany this project. And we also do some development on demand for our customers, where they use some special mix or special powders, or they develop something for very special, secret, or sensitive applications like nuclear, military, etc. So this project was implemented in the frame of on-demand service, and it took about, let's say, 12 months to do this job with all the tests performed by Matthias. First, when we identified this cerium-doped zirconia, we could find that strength of the material was very low compared to the yttria zirconia. Yes, we won in toughness, as you can see on this diagram. Strength, it's Y axle, and toughness is X. So it's toughness in function, in relation with strength. So we had to deal with something, we had to add something to the mix to increase the strength, at least to be comparable to the strength of the yttria, and to increase a little bit more the toughness. To do this, first, we had to introduce alumina nanoparticles, very fine particles of alumina, to this mix to increase the strength of the material, but it didn't increase the toughness. So to increase the toughness, we had to use some whiskers or platelets from aluminate strontium, and these whiskers could increase the toughness of the materials. So altogether, provided us possibility to develop the target material you can see on the diagram, which at the same time was good strength and good toughness. This material is composed of 84% in volume of cerium zirconia, about 8% in volume of alumina, and about 8% of volume of strontium aluminate platelets or whiskers. Now we have to see if this material was printable, if we can print with this material, which is another challenge, because as I explained to you, we print this powder mixed with the photosensitive binder. So we have to be able to recoat this material. We have to be able to cure or to polymerize this material with a UV laser. And we have to be able to build some shapes. I mean, this material has to be cohesive, has to be shapeable, and it's a real challenge of the printing expertise we have in-house. It was developed, it was done. We act on the presets. We could develop some new parameters for the printer to deal with this challenge, and we could print the bars and some test bars and some discs first to see the behavior of the printing step. But as I told you, the printing is just the first step of the total production process. So how the debinding and sintering will impact this? And this is another challenge for which we have to have ceramic expertise. And that's why I explained to you that the company started with the ceramic engineers, and our roots, our genesis is ceramics. So having this ceramic knowledge, having this ceramic expertise, having these resources in-house helped a lot to develop this post-process steps, which is sintering mainly. Because sintering regime, sintering temperature, soaking time change a lot the property of the material itself. As you can see on the diagram, you see 3 lines. The green one is our reference material, which is called isostatic pressed zirconia. And this is like a reference for us to follow, because at least printed material has to be similar, equivalent to this reference conventionally manufactured material. Of course, this is simplified diagram because we did much more tests, not just temperature T1 or T2 was tested, but also soaking time, different ambience, etc., environment. But here I just give you the results of the study where we found out the sintering temperature T2, which is really close, roughly similar to the reference material conventionally manufactured by cold isostatic pressure. It was implemented on the beams of 40 on 4 on 3 millimeter dimension, and we could obtain the Weibull modulus 40, which is very nice for the mechanical properties of ceramics. So I explained about the aging, toughness, strengths. I explained about the other mechanical properties, but what about the deformation? Because you know, in dental industry or implant, and ceramic is considered as a brittle material, it's not plastic material, it's not like your plastic or rubber. You cannot bend it, you can just, I mean, when you bend it, you just break it down. So the challenge also was, and the characterization target was to understand how this material is defect resistant. Typically, we use this Vickers test when you have a point tool. You give the shock on the surface of the ceramic material, and you see how big is, or how the smallest shock which damages the whole part. The diagram is a little bit complicated, but what is interesting to understand in this surface of inclined surface, which leads which is at the border of plastic transformation of the material. More this surface is big, more material is plastic. So it means that on this diagram, when we tested this new material, ceria-doped zirconia material, we could obtain the ceramic, which is the behavior of which is much more better than for traditionally used zirconia. It means that with this weight modulus of 40, with this strength and toughness, we could obtain the material which is closer to casted iron than to ceramics. Here on this diagram, you can see 3 yttria zirconia in blue area, and the orange one is the new ceria-doped zirconia composite, which allows the critical defect tested by Bicker's method of 100 microns instead of only 1 micron of critical defect for the traditional used zirconia. This picture on the left gives you the understanding of what I'm speaking about. It means that in some way you can even a little bit bend this ceramic material, which is really new for this field. At least the critical effect is just 100 times more than the critical defect of traditional used material. So the conclusions of this study, which was implemented with Matisse, and this collaboration allowed to join the expertise of materials from this national lab and expertise of 3D printing and ceramic behavior from us, we could develop the material properties after sintering, so of the final advanced ceramic, the same properties even better than for traditionally used cold isostatic pressure method. And this is very interesting for the industrial people. If you want to manufacture, if you want to go to the industrial integration of this, not only research, because from the beginning our company started industrial integration. So these printers were developed to go easily from the small one, small size of the printer we have, it's 100, 100, 150 millimeters, so we can print fancy things already on this. But we can also scale up easier the production to the medium range printer, which is 320, 200 millimeters, and to the big one, which is the biggest one in the world, it's 600 on 600 on 300. All of them use the same slurry. All of them use the same lasers. All of them use the same interface. So it's very easy to scale up, to integrate industrially the product you develop in lab to industrial production. And this is really interesting for dental implants, for example, because you break down the cost by a lot using the small printer or the big printer. For the time of the printing, just to make you some figures, to give you some figures, when you print the dental implants on the big platform of our ultimate biggest printer, the time of printing per implant is about 1 minute, 20 seconds. So it's very quick and comparable to the conventional, traditional manufacturing method. The cost of materials, of course, we can speak on the materials, on the consumables cost, because in each country, the other costs are really related to the local reality. But the material cost per implant is less than $1 for the ceramic zirconia implant. So fast printing process, large printing area, easy use of the printer will help to introduce this technology to at the industrial level. And of course, when we speak industry, we speak automation, because these kind of parts need to be very repeatable in quality. So human factor impact has to be reduced. So in the future, and we are developing the concept of the printing farms with the automation of the unloading process, with the automation of slurry filtering process, to make this process really industrial. Just not only standalone printers, but network of printers working in harmony in the printing farm. So that's all about the material. Just small introduction on next year in Europe, we'll have the conference and exhibition of European Ceramic Society. it will take place in Lyon, in INSA. So you guys are welcome to come to Lyon next year, to the City of Lights. And it can be also, we can also organize the visit of our facility and maybe of the Ceramic Research Center in Limoges. Thank you very much for attention. My contact data are indicated on this slide, so I invite people, if you have any questions, any requests, any information I couldn't share here, just send me email, give me a call. I will be available for all these requests. Thank you very much again for attending this webinar, for inviting us, and see you later.
Hello. Thanks a lot.